Hey guys, this video is created by group number 1, the Matrix, and our topic is crystal system, which belongs to our main topic, solid state physics, which is a state of matter. Now basically there are three states of matter: gas, liquid, and solid. In gaseous state, the molecules of the matter are distantly apart from each other, so they have too much intermolecular spaces between them. Here we can take steam as an excellent example. But in liquid state, the molecules of the matter are packed with each other, but they do have some intermolecular spaces between them, so we can take water as a great example. And in solid state, the molecules of the matter are very closely packed with each other, hence the intermolecular spaces between them are really less. Here we can take ice as a great example. Now if we move from gaseous state to liquid state and from liquid state to solid, the intermolecular spaces between them starts reducing. As the interatomic separation starts reducing, it can result in two types of arrangement: irregular arrangement, which leads to amorphous solid, and regular arrangement, which lead to crystalline solid. And these are the two major types of solid. So, in amorphous solid, the arrangement of constituent particles such as atoms, molecules, or ions in such a solid has only short range order. In such an arrangement, a regular and periodically repeating pattern is observed over short distances only, while in crystalline solid, they usually consist of a large number of small crystals, each of them having a definite characteristic geometrical shape in a crystal. The arrangement of constituent particles, such as atoms, molecules, or ions, are ordered. Now here we can see the basic structure of amorphous solid and similarly the basic structure of crystalline solid. Now let us see the properties of crystalline solid and amorphous solid, differentiating between each other pointwise. First of all, shape. Crystalline solid have definite characteristic geometrical shape while amorphous solid have irregular shape. Second of all, melting point. Crystalline solids melt at a sharp and characteristic temperature while amorphous solid gradually soften over a range of temperature. Third is the cleavage property. When crystalline solid cut with a sharp edge tool, they split into two pieces and the newly generated surfaces are plain and smooth, while when amorphous solids are cut with a sharp edge tool, they cut into two pieces with irregular shapes. Here, fourth is the heat of fusion. Crystalline solid have a definite and characteristic heat of fusion, while amorphous solid do not have a definite heat of fusion. Fifth is the anisotropy. Crystalline solids are anisotropic in nature, while amorphous solids are isotropic in nature. Sixth is the nature. Crystalline solids are true solids, while amorphous solids are pseudo-solids or supercooled liquids. Now, seventh is order of arrangement of constituent particles. Crystalline solids are long range ordered, while amorphous solids are only short range ordered. Now let us move to the crystal structure. A crystal structure is a combination of lattice, which are imaginary and periodic array of points, and bases, which are atoms or molecules. So in this figure, the tray represent lattice and the eggs represent bases. Both of them combine to form a crystal structure, as shown in the figure. Now what is a crystal system? A crystal system is a method of classifying crystalline substances on the basis of the unit cell. And unit cells are smallest geometrical unit by the repetitions of which complete crystal structure or lattice is produced, as you all can see in the diagram. And in this figure we can see lattice parameters. X-axis intercepts A, Y-axis intercepts B, and Z-axis intercepts C. Here we can also see interplanar angles. XY axis equals to angle gamma, YZ axis equals to angle alpha, and ZX axis equals to angle beta. Now we can see that there are 7 types of crystal systems based on geometry: cubic, rhombohedral, hexagonal, tetragonal, orthorhombic, monoclinic, and triclinic. And here we can see some examples for each type of crystal systems. Now let us see the types of unit cells. There are three major types of unit cells: simple cubic unit cell, body centered cubic unit cell, and face centered cubic unit cell. Simple cubic unit cells have an identical number of atoms on each corner of the unit cell, while body centered cubic unit cells have an atom sitting on each corner just like the simple cubic unit cell with an additional atom at the center. And face-centered cubic unit cells contain the atoms in the corner like simple cubic unit cell plus an additional atom centered on each face of the cube, as we all can see in the diagram. Now let us discuss about Bravais lattice. So there are 7 types of crystal system based on geometry and 3 types of unit cell based on orientation of atoms. So there should be 7 multiplied by 3, which is equal to 21 crystal structure, but that's not possible. We only have 14 permissible crystal structure such that the environment about each point remains identical, known as Bravais lattice. It was suggested by a French crystallographer, Auguste Bravais, in 1884. Now in this table, we are going to see possible number of unit cells of each crystal system. First one is cubic, which has 3 possible unit cells: simple, face centered, and body centered. The second one is tetragonal, which has 2 types of unit cell, which are simple and body centered. Third one is orthorhombic, which has 4 possible unit cells: simple, body centered, base centered, and face centered. Fourth one is monoclinic, which has 2 possible unit cells: simple and base centered. And the remaining 3 crystal system, which are triclinic, hexagonal, and rhombohedral, all of them have only one possible unit cell, which are all simple. 7 crystal classes with 4 possible unit cell types. Symmetry indicates that only 14 3D lattice types occur. Now let us move to the properties of simple cubic, body-centered cubic, and face-centered cubic unit cells. First, number of atoms per unit cell. Second is the coordination number. Third is atomic radius. Fourth is packing fraction and efficiency. And the fifth is density. Now we will see packing factor of simple cubic unit cell. In simple cubic unit cell, the spheres touch along the cell edge. Consequently, the edge length is 2 atomic radii, A equals to 2R. The properties of simple cubic unit cells are: number of atoms per unit cell equals to 1 atom per unit cell, coordination number equals to 6, atomic radius equals to 0.5 multiplied by A, and packing fraction and efficiency is 52%, as shown in the diagram. Now we'll move on to the packing factor of body-centered cubic unit cell. For the body-centered cubic unit cell, the spheres make contact along the body diagonal BD, which is 4 atomic radii, each yellow arrow in atomic radius, that is BD equals to 4R, as shown in the figure. The body diagonal is related to the face diagonal FD and the edge cell A by Pythagoras theorem. The properties of the body-centered cubic unit cells are: number of atoms per unit cell is 2 atoms per unit cell. Coordination number is 8. Atomic radius is under root 3 by 4 into A, which is equals to 0.433 A. And the packing fraction is 68%, as shown in the figure. And finally, we'll see packing factor of face-centered cubic unit cell. Particles contact in the face-centered cubic unit cell is along the face diagonal FD. The face diagonal is 4 atomic radii, which is FD is equals to 4R, and is related to the unit cell edge length A by the Pythagoras theorem. So the properties of the face-centered cubic unit cells are: Number of atoms per unit cell equals to 4 atoms per unit cell. Coordination number equals to 12. Atomic radius equals to under root 2 by 4a, which is equals to 0.354a, and the packing fraction is 74%, as we all can see in the diagram. Alright guys, thanks for watching this video created by group number 1, the Matrix.